Welcome. So in this session, we are going to discuss about initial value problems and boundary value problems for the case of second order linear homogeneous differential equations. So an initial value problem IVP consists of finding a solution y of the differential equation that also satisfies initial conditions of the form y at x naught equals to y naught and y prime at x naught equals to y1, where y naught and y1 are given constants. So, example, solve the initial value problem so y at 0 is 1 and y prime at 0 is 0. So let's see how we work out this. Now, the first thing is to get the general solution of the differential equation. So let y be e raised to power rx with the solution. So this means derivative r e raised to power rx and second derivative r squared e raised to power rx. So using these values in the differential equation, we have r squared e raised to power rx plus r e raised to power rx minus 6 e raised to power rx equals to 0. So we'll have r squared plus r minus 6 factor out e raised to power rx will be equals to 0. Now this means that auxiliary equation is r squared plus r minus 6 equals to 0, since e raised to power rx can never be 0. So product minus 6, sum 1, so numbers minus 2 and 3. So we'll have r squared minus 2r plus 3r minus 6 equals to 0. Common here is r minus 2 plus 3 into r minus 2 equals to 0. So which means r minus 2 r plus 3 equals to 0. So this means r equals to 2 or r equals to minus 3. So which means that y1 of x is e raised power 2x and y2 of x e raised power minus 3x. So general solution is y equals to c1 times y1, c2 times y2, which is c1 e raised power 2x plus c2 e raised power minus 3x. So y c1, actually y of x, now with the given conditions, we need to get y prime to be 2c1 e raised power 2x minus 3c2 e raised power minus 3x. So when y is 0, we'll have c1 e raised power 2 times 0 plus c2 e raised power minus 3 times 0, which is c1 plus c2, and this should give us 1. Call this one equation 1. And then y prime at 0 will be 2c1 times 0 minus 3c2 minus 3 times 0, which implies 2c1 minus 3c2. This y prime at 0 was given as 0 in the given initial conditions. So from 2c1 equals to 3c2, which means c1 is 3 over 2c2. So call this one equation 3. So using 3 in 1, we get 3 over 2c2 plus c2 equals to 1, which means multiplying through by 2 will be 3c2 plus 2c2 equals to 2. So 5c2 equals to 2, which means c2 equals to 2 over 5. And then so c1 will be 3 over 2 times 2 over 5, which is 3 over 5. So hence the solution of the given initial value problem is y of x equals to c1 is 3 over 5 e raised power 2x plus c2 is 2 over 5 e raised power minus 3x. And then example 2, y double prime plus y equals to 0. Y at 0 is 2. Y prime at 0 is 3. Solution. So let y be e raised power rx be the solution. So which means that y prime is r e raised power rx, and second derivative will be given by this. Using these values in the differential equation, we'll have r squared e raised power rx plus e raised power rx equals to 0. So r squared plus 1 e raised power rx will be 0. Auxiliary equation is r squared plus 1 equals to 0, since e raised power rx is always non-zero. So i.e. r is plus or minus I, because this will be r squared equals to -1. So square root of -1 is plus or minus I. So this is a case of complex. So whereby, remember, if you have complex root of this form, solution is usually e raised power alpha x c1 cos beta x plus c2 sin beta x. So our alpha in this case is 0, so this can be written as 0 plus or minus 1i, and beta is 1. So therefore, general solution is y of x equals to e raised power 0 times x, so that's alpha, c1 cosine of x because beta is 1, plus c2 sine of x. Now 0 times x is 1, is 0, e raised power 0 is 1. So the general solution is c1 cos x plus c2 sine x. But you have been given the initial conditions. So y prime of x is negative c1 sine x plus c2 cos x. So y at 0 is c1 cos of 0 plus c2 sine of 0, which will give us c1, and this from definition is given by 2. So we have one value of unknown is 2, and y prime at 0 will be negative c1 sine 0 plus c2 cosine of 0, which will be c2, and from definition, y prime at 0 is 3. So this is the second unknown. So hence, the particular solution of the given initial value problem is y of x, c1 is 2, cos x plus c2, which is 3, sine x. And now let's discuss about boundary value problems. BVP. So a boundary value problem for this equation a y double prime plus a y prime plus by equals to 0 consists of finding a solution of the differential equation. Actually, you can just say a boundary value problem for second order linear homogeneous ordinary differential equation consists of finding a solution of the differential equation, a solution y of the differential equation that also satisfies boundary conditions of the form y at x naught equals to y naught and y of x1 at x1 is y1, but not unlike initial value problems, boundary value problems do not always have solutions. Now let's give an example. Solve the boundary value problem y double prime plus 2y prime plus y equals to 0, subject to y at 0 is 1 and y at 1 is 3. So as usual, you get general solution. So let y equals to e raised power rx be the solution. So this means the derivative is r e raised power rx, and the other derivative is r squared e raised power rx. So replacing, we'll get r squared e raised power rx plus 2r e raised power rx plus e raised power rx equals to 0. So we have r squared plus 2r plus 1 e raised power rx equals to 0. Now, r squared plus 2r plus 1 equals to 0 is the auxiliary equation. Since this is always non-zero. Now, product 1, sum 2 numbers 1, 1. So we'll have r squared plus r plus 1 equals to 0. So this and this, r into r plus 1 plus 1 into r plus 1 equals to 0. So r plus 1 equals to 0. So r equals to -1, -1. Repeated root. So solution is y of x equals to c1 e raised power -x plus c2x e raised power -x. This is a general solution. Now, when x is 0, we'll have c1 e raised power -0 plus c2 times 0 e raised power -0, which is just c1. And this would give us 1. So we have one of the unknowns. When y is 1, we'll have c1 e raised power -1 plus c2 times 1 e raised power -1. So which is c1 e -1 plus c2 e -1 equals to, by definition, we have to get 3. But since c1 is 1, so it means that e raised power -1 plus c2 e raised power -1 equals to 3. So c2 e -1 equals to 3 minus e raised to power negative 1. And then C2 will be 3 over e negative 1 minus e negative 1 over e negative 1, which is 3 e raised to power positive 1 minus 1. So this is the value of C2. Therefore, the particular solution of the given boundary value problem is y of x equals to C1 is 1, so we'll have e raised to power negative x plus C2 is 3e minus 1 e raised to power times x e raised to power negative x. So this is the final solution. Thank you.